Hi, in this video we'll talk about two examples of energy balance in radiation. Let's talk about the idea of energy balance. The idea is very simple. It means that when you have the temperature being constant, that means you reach thermal equilibrium, but then there's always incoming energy coming in, and you're also radiating the energy out in every second. That means powered. They must be equal in amount because again, you don't change your temperature. That means the net change of your energy is zero. So that is to say, the power in will equal to the power out. And this is an illustration in terms of a diagram that shows you how it can be done through the incoming light intensity and the one that you radiated back to the surrounding. Okay, so let's look at this question. So it said assuming the Earth's surface has a fixed temperature, so like we said, a constant temperature, and it radiates as a black body, so that means the emissivity, we can take it as 1, literally 1. And the average intensity that coming to reach the Earth's surface is like the one that we did, which has a number of 245 with that unit. And it asks you to write down the equation expressing the fact that the energy will be balanced or the power will be balanced. So the way that I would like to do is I will start with power in equal to power out. So this is my hint. If you'd like to try it yourself, please pause the video now and try it.
A few moments later.
Alright, so for the power that coming in, it would simply be IAV times the area, because this again is not power, it's just intensity. If you look at the unit, is watts per meter square. So that's why we have to multiply the area, and this area is regarding the Earth surface, so the spherical surface. As for out, then it is the radiation equation. That's the Stefan-Boltzmann equation. So simply by recalling the equation, right, this will be it. And the good thing is you find out the 2a will simply be cancelled out because they are referring to the same thing here. So both are the surface area of the spherical object, the Earth we are talking about now. So now we can just substitute the number, or I guess I'll just substitute the equation first. All right, I'm not sure what they want. I think they want equation. So yeah, I don't want to substitute the number, but I will put the symbol. As for emissivity equal to 1, so we can just take it away. And this is a constant we can find out, and T is not mentioned, but then we already know it's a fixed temperature, T. For part B, it asks us to calculate the temperature basically if it really stays constant. So we already know that the solar radiation reaching the Earth on average will be 245 according to the question. So left hand side will be 245 simply. And for the sigma, we have to refer it back to the data booklet, which you can find. By the way, you need to learn how to find the number. It should be on the fundamental constant that page. And you'll be able to find the Stefan-Boltzmann constant 567 negative 8. Right, it's quite easy to remember. 567 negative 8. Alright, times T to the power of 4. So you just have to solve it using calculator. So you should find the answer of 256 point something. Okay, which you may find, hey, it's a lot, isn't it? But then if you think about that, it is gonna be in Kelvin scale. So let's just see what it would look like when you change to degrees Celsius. So what I have to do this time is you have to do minus. Okay, so that's going to be negative 16.6 degrees Celsius, right? But then still, this is not acceptable because everyone knows on Earth, our temperature on average is about, I guess, 15 to 20, or at most 25, right? So 15 to 25, I think is a good guess in terms of average. It cannot be negative 16. So what's the problem? And this is the best part of this question because this is literally what scientists calculate, right? We predict using our model to think that, hey, the temperature should actually be 16.6 if we keep it constant. Okay, it should be constant because we shouldn't be facing like the average going up and down like constantly, right? So it should be quite close to constant at least. So 16.6 should be a good guess, and 245 is like a measurement you take. So what's wrong then? The problem is, if you find out your result is contradictory to your reality, probably is either, well, other than human mistake of course, then would be your model has some issue. Maybe your assumption is not really like correct, or has a big discrepancy from the reality. So the answer is that if you try to think about for part C, which is commenting your answer, then obviously the first thing that you want to say is that it is much lower. Right? The answer in part B is much lower than the reality, and so you have to think about the reason. I'll give you some time. Okay, so the answer is something to do with our model once again. So let's look at the diagrams again. So what we think of is when the light coming in from the sun as an intensity I, and then the one that actually received by the earth is actually 1 minus alpha times I, and those will be the one that receive. At the same time, the earth will also radiate by radiation, the Stefan-Boltzmann equation, with the same amount. So that is the equation that we calculated. However, we are expecting the temperature to be higher. Alright, once again, if you compare our answer -16 to our usual perception about 20 degrees Celsius, so there must be something that keep our earth warmer for some reason. And the answer is the later part here, alright, the radiation. Because not all of this radiation away from the earth will be emitted to the surrounding, to the space, and it is gone forever. Actually, some of those will be reflected again onto the atmosphere and it got radiated back again to the earth. And that is the idea of greenhouse effect. And if you remember earlier, we talked about the calculation for the EM wave, maximum EM wave in intensity emitted by our body, which is infrared. Same for the earth as well, because when you try to think about an object in around our body temperature or 20 something degrees Celsius, it's also emitting the infrared the most. And if you know about the greenhouse gases, those are the gases that can effectively absorb the infrared and re-radiate in all directions. So this is something that we, using this model, we have not considered, and that's why we overestimate the amount of energy or power that got radiated away from the earth. So that's why in reality, by considering the greenhouse effect and also greenhouse gases, the temperature is way higher. And that also means, in fact, greenhouse gases are not totally bad guys. All right, think about that. Without greenhouse gases on Earth, this -16.6 degrees Celsius is the temperature, and this obviously is not suitable for human to live. All the water, ocean, they all become ice. Right? It's not possible for not only human but also for many other things to live as well, including our body. So having CO2 and also other greenhouse gases is certainly essential for a planet to be livable by us and also most of the animal that we see. But then the problem is really, later on in the other video we talk about, is really about too much of those greenhouse gases will cause the temperature to be too high, basically. That's all for this part of video. I hope you enjoy it. In the next part of video, we'll talk more about the greenhouse effects, the mechanism of how it works in more details. Before you move on to that video, I would like you to watch this video from 60 Symbol. They have really good explanation on how greenhouse effects could be explained using different animation and also show you calculation as well. It's somewhat related to what we cover in this part of video. So please go ahead and watch it. I'll put the link in the description below and also on my playlist as well. I'll see you again in the next video.